Page 5 of binomial expansion. We're going to start here with reference to the formula sheet of the of MathSL. So on the formula sheet, you are going to see pretty much this here. On the left side, you have the binomial a plus b to the nth power, and on the right side, you have a string of terms. How many terms do you have here? Well, we have 1, 2, 3, 4 terms. What are these dots here? The dots indicate that there's a bunch of terms in here that they are not showing. They're only showing certain terms. Which terms are they showing? They're showing the first term, obviously. This here is the second term. This here is the last term. And this here is what they call the general term. The general term is expressing a formula with the variable r, and this can be any term in the sequence. It even could be the first term or the last term. But anyway, they call it the general term, and here they kind of put it in the middle, and they separate it from the rest of the terms with dot, dot, dot to show that it could be anywhere. The way we can tell this is the general term is because we can look at it, and in each part of the term, the Pascal's triangle coefficient, the a term and the b term, you can see references to the variable r. What is this variable r? The variable r is a number which tells us which position in the expansion we are at. Okay, and the way they number each of the terms is starting from 0, and then they count up from left to right until they get to n. Remember, n is the power of the binomial, and remember that if the power is n, we have n plus 1 terms. If you have n plus 1 terms, you might think, hey, n plus 1 terms, that means the last term would be n plus 1. Well, it would be if we started counting from 1. But we can't start counting from 0. Our first term is actually called r equals 0 term. The second term is r equals 1. And so the last term, even though it's the n plus first term, it's called the nth term. Okay? So the general term is actually the rth term. Which position in this expansion is the rth term? It's in the position r plus 1, because the position number is always one more than the r number. Okay? So the r tells us exactly where in the sequence we're at. Okay? Just start from the beginning, count that one as 0, and then go up one successively until you get to the general term, the rth term. Okay? All right. Here is another form, which is a little bit friendlier, but unfortunately this one is not on the formula sheet. So I don't really see much point in, getting used to using this because you're not going to have it on the exam. Do you see how it says t r plus 1? The t here would be the term. R plus 1 is saying, hey, the r plus 1th term. And if you look at this, you can get the relationship between, hey, if I know it's the 11th term, r plus 1 is 11, that means that r is 10. You can see that the ordinal number of the term is one more than the r value. So that's kind of useful, but you don't get it on the formula sheet. Here it is in sigma notation, and I won't spend too much time on that because we haven't talked about sigma notation in class yet because we skipped this chapter. So forget that for now. Okay, let's move down to 7c1. I'm kind of sorry that I am, showing the work like this because I would like to write it as you're looking at it, but it's really hard to write these problems out fast enough and neat enough, so I got to do it this way. Okay, sorry about that. So first we're going to do the expansion of part A, which is 1 plus 2x to the 11th power. The a term, or the first term, is 1. The second term is 2x. The n value, or the power, is 11. With these three inputs, we can generate the whole expansion, but they only ask us for the first 3 terms and the last 2 terms, and they'll do this sometimes on the exam too. So the first and last term are kind of the easiest ones to do, and then as you move into the middle, they get harder and harder. But usually the second and the next to last ones are not that hard either. The third one's kind of hard. It's kind of a challenge. So first of all, we'll look at the Pascal's triangle coefficient for each one. When you have the first or the last term, we know that the Pascal's triangle coefficient is 1 and 1, right? What about the second Pascal's triangle coefficient, or the second to last Pascal's triangle coefficient? Well, we also know that the second number in the Pascal's triangle row is always the n value. So since the n value is 11, we can put 11 at the Pascal's triangle coefficient for the second term and for the second to the last term. Now we'll get to the third term and show why it's the most challenging. Because the Pascal's triangle coefficient for the third term is, we don't know. So we could calculate it using the 11 chooses 2 combinations function. So we could put this in the calculator and generate it, okay? Now in this case, it said not to expand our answer, so we could just kind of leave 11 chooses 2 here. Let's move on to the a values. The a value is 1. So we don't really need to do anything with the a value because the a value in the first term would be 1 to the 11th, but 1 to the 11th is 1. 1 to anything is 1. So in the second term and every single other term, the a value doesn't really appear because it's always 1 to a something power. It's always going to be 1. So now let's look at the b term, which is 2x. The 2x term is going to be in the first term, it'll be 2x to the 0th power. 2x to the 0th power, anything to the 0th power is 1, so it just kind of disappears. 2x in the second term is going to be just 2x. And I did not put parentheses around my numbers here. I wrote them in different colors so you can kind of see that they were different numbers. So this is 11 times 2. I should put a dot here or maybe put parentheses, but I just wanted to show the pattern using different colors. Okay, so like the red is Pascal's triangle coefficient, and the brown is the b term to a certain power. Now look at the third term. I have 2 squared x squared. The way you would normally start writing the b term would be maybe parentheses 2x to the squared power, like for example 2x squared. But when you have things in parentheses to a square, you must distribute the square to each one of the elements that's in the parentheses. So it would be 2 squared x squared, right? That's why I got 2 squared x squared. And toward the end here, I have 2 to the 10th, x to the 10th. And then I have 2 to the 11th, x to the 11th for the exact same reason, right? So that's it for A. That's how you build 1 plus 2x quantity to the 11th, okay? Let's move on to C. Okay, so here's C. Wow, that looks like a challenging one, doesn't it? So in this one, we have n equals 20. So that means that the Pascal's triangle coefficients go 1, 20, something, blah, 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 blah. And then when it gets to the second last one, it's 20 again, and then 1 again, right? So the only challenge is the third Pascal's triangle coefficient, which we could find by doing 20 chooses 2 on the calculator, okay? So I put the Pascal's triangle coefficients in red. Okay, then we look at the a value, which is 2x. Now, I put the 2x term in purple, and you can see that 2x starts out to the 20th power here, and then the next term it's the 19th power, next term it's the 18th power, next term it's the, well, we've skipped a bunch, but the second to the last term is to the first power, and the last term is to the 0th power, so 2x, the purple 2x just disappears. You see how I put the 20th power on both the 2 and on the x, because when you first write it, you might write 2 to the x to the 20th, and then you need to say, okay, I'm going to distribute the 20 power to both the 2 and the x, and that's why you get 2 to the 20th, x to the 20th, x to the 20th, right? So that's how you get the purple numbers here. Now, what about the brown part? The brown part comes from the second term, which is minus 3 over x, or negative 3 to the x. it's often useful to pretend that this minus sign actually is a negative sign that goes with 3x, 3 over x, and assume that it's like addition of a negative number. And then what you do is you take the negative 3 over x and you put it in for the b. And remember, the first b term is b to the 0, so it doesn't matter what b is for the first term. The second term, it would be b to the first power, so it would be just negative 3 divided by x. And notice I put negative 3 in parentheses to show that it's a multiplication of negative 3 and not a subtraction of negative 3. In the third term, I have negative 3 in parentheses squared, and in the bottom I have x squared also. Finally, in the next to last term, I have negative 3 in parentheses to the 19th power, and the bottom is also x to the 19th power. Same thing as when you have 2x quantity to the 20th. When you have negative 3x to the 19th, you have to distribute the 19th power to both the 3 and to the x and also to the negative sign. Okay, so it's negative to the 19th power. A negative to the 19th power is negative, right? 3 to the 19th is 3 to the 19th, whatever that is. X in the denominator to the 19th power is also x to the 19th in the denominator, or you could write it as in the numerator as x to the negative 19th. Finally, the last term, no red number because the Pascal's triangle coefficient is 1. No purple number because the a term, 2x, when you take it to the 0th power here, it disappears also. Finally, you just have the brown term, and we have the brown term to the 20th power. By the way, what is negative 3 to the 20th power? I'm not sure, but it's positive, okay, because the negative to the 20th power becomes a positive instead of a negative. Okay? So you could write this as negative 3 to the 20th power, and then x to the negative 20th power if you put x in the numerator. Okay? Now, should this negative be inside the parentheses or outside the parentheses? It has to be inside because it's part of the b term. If it's part of the b term or the a term, put it inside the parentheses before you take it to the power. Okay? All right, let's move on to the next one, which is number 2. Okay, so it says, without simplifying, write down the 6th term of 2x plus 5 to the 15th. This would be a really easy exam problem, but they might ask you something like this. So first what you're going to do is you are going to write the Pascal's triangle coefficient. I'm doing it in red here. Since they asked for the 6th term, I know that the 6th term is actually one more than the r value. So 6th term is an r value of 5, so I fill in 5 for the r here. Because remember, this is n chooses r. So 15 chooses 5. Why 15? Because n equals 15. Why 5? Because it's the 6th term, and the 6th term is r equals 5. Then I put the a value, which is 2x in parentheses, to the 10th power. Why did I put the 10th power? Because in the general term, look at the general term up here. I don't know if I went over this when we did talk about the general term. But if you look at the general term, look how the exponent of the a value is n minus r. And then the exponent for the b value is simply r. Isn't the exponent for the b term much easier to remember than the a term, right? The b term exponent is just r. The a term exponent is n minus r. How are you supposed to remember that, right? Well, you don't have to because it's written in the formula sheet, right? Let's go back to number 2 now. Okay, so we know that the purple a term is going to have the exponent n minus r. N minus r, so 15 minus 5, so it's 10. So 5 is going to have the exponent. 5, by the way, is the second term. Do you see the b term is 5? So that's why this is 5. The exponent is going to be r. R is 5, right? So how can you check to see that you did your exponents right? Well, one brief check, which isn't 100%, but it's pretty good, is you can add the two exponents together, and that should give you your n value. So 10 plus 5 gives us the n value. So it looks like we probably got our exponents right. Okay, so that is the answer for part A. Part B asks for the 10th term of this one here. So we have the n value at 17. We have the a value at x. The b value is negative 2 over x. Okay, so the Pascal's triangle coefficient we're going to use here is going to be related to the 10th term. I sometimes have trouble remembering that for the 10th term, the R value is 9. If you don't remember, one thing you could do is you could write out on your paper, like, okay, first I'm going to write out the the term ordinal number. So you can say, oh, I know it's 1, 2, 3, blah 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 blah, to the n plus 1th term, right? And then underneath it, you could write, I'm going to write the R numbers. So R equals 0, R equals 1, because we know that the first term always has an R value of 0. And so the last one would be 1 less. Do you see how this is 1 less than this one, this is 1 less than this one, this is 1 less than this one. So under the n plus 1th term, we would use R equals n, right? So if you write that out, it's pretty easy to see that the R value is 1 less than the ordinal number for the term. So since the ordinal number for the term is 10, then we want the R value to be 9. So there's our red 9. And there's our brown 9 here, because we know that the R value is also the exponent of the B term. What's the B term? Negative 2 over x. We keep the subtraction sign as part of the B term because that accounts for it, and then you could just like forget about it, okay? Purple would be the one that's kind of hard to remember. It's n minus R term. So it's 17 minus 9, so it would be 8. And as a final check, you can take the 8 and 9, add them together, and you get 17. And guess what? 17 is the n value, which is a way to check to see that you kind of have this right. Okay? So that was number 2. Let's move on to number 3. All right, here's number 3. On number 3, it says, consider the expansion of x plus b to the 7th power. Write down the general term of the expansion. Okay, the general term of the expansion is going to look like this. This is pretty much copied from the formula on the formula sheet. N chooses R, a to the n minus r, b to the r. Okay, so I just rewrote what's on the formula sheet. Then I'm going to fill in everything I know, because it's once the general term for this expansion. So I do know some things about this expansion. I know, for example, that n equals 7. I know that the a term is x. I know that the b term is b. Isn't that a little bit confusing that we call this the a term and this is the b term, and the b term actually is b? It's like, oh, I'm talking about the b term. But what is the b term? It's b. Oh, no, I asked you what the b term was. Okay, it's kind of confusing that we call this the b term and it is b. But that's why I put a in quotes is equal to x, and I put b in quotes is equal to b, because in this case, b is b. Okay, and n, of course, is 7, because n is the exponent. So let's fill in what we know into the general term. So the general term has n chooses r, or 7 chooses r. Do we know r? No, we don't, because they're not specifying the r yet. Then we have the a term, which is x, and it's to the power 7 minus r. Why 7 minus r? Because it's n minus r. Remember, in the general term, the exponent for a is n minus r. The exponent for b is simply r. So the exponent for the b term, which is just b, is r. Believe it or not, it doesn't seem like we did anything, but that is the answer to the part A. It says write down the general term of the equation. There it is right there. Part B says find b given that the coefficient of x to the 4th is negative 280. This is something backwards to what we've done so far. We usually knew what the a term and the b term were, and then we figured out what the 7th term was, or whatever. In this case, they're telling us what one of the terms is, which is negative 280 times x to the 4th, because the coefficient of the x to the 4th term is negative 280. We don't know exactly what b is. They want to know what b is. So now we know why they left b here, because actually they didn't know what b was, so they left it as b. Okay. So we know that the term they want is negative 280 x to the 4th. They're asking us what b term would make the x to the 4th term have this coefficient. Well, why don't we take the general term x part of the equation, x to the 7 minus r, we'll write it down here, and we'll set it equal to x to the 4th. If we do that, we'll be able to figure out what r is, right? So we say, okay, x to the 7 minus r equals x to the 4th. That means we can equate the exponents, right? So 7 minus r equals 4, which means that r equals 7 minus 4 equals 3. So r equals 3. Now that we know that r equals 3, we're going to go back and put 3 in here, put 3 in here, put 3 in here. We're going to get 7 chooses 3 times x to the 4th times b to the 3rd. We still don't know what b is. It's kind of like an unknown. That's not actually a b there. Equals negative 280 x to the 4th. Okay, and so of course the x to the 4th match, because that's the whole reason why we put r equals 3, okay, to make the x to the 4th match. So we know this matches with this. Now this purple expression and this purple expression multiplied together, combined together, must equal negative 280. Okay, so now what I'm going to do is I'm going to write a separate equation, which is going to be 7 chooses 3 times b cubed. Oh wait, 7 chooses 3. What is that? Remember, 7 chooses 3 could be found using the combinations formula that's on the formula sheet, which is n factorial divided by r factorial times n minus r in parentheses factorial. It could also be written as 7 times 6 times 5 times 4 divided by 4 times 3 times 2 times 1. And we can cancel stuff out, and what we're left with is 7 times 5, which is this 35. So you can see, even though a combination like this might look intimidating, once you cancel stuff out, it's basically a 4th grade multiplication problem. Okay, so then you take your 35 and you expand the 7 chooses 3, or you simplify it into 35. The x to the 4th you ignore because we're not interested in the non-purple part. We just want the purple part for now because we know that x to the 4th is equal to x to the 4th. We want to know that the purple part is equal to the purple part, and we'll be able to figure out b cubed because of that. So 35b cubed equals negative 280. Then we divide both sides by 35, and then we get negative 8 left on the right side and b cubed on the left, negative 8 on the right side and b cubed on the left side. Then we take the cube root of both sides and we get b equals negative 2. Why negative 2? Because it's negative 8. Negative 2 times negative 2 times negative 2 yields negative 8, right? So we have figured out what b is. It's negative 2. Okay, we're done. Okay, let's move on to number 4. Number 4. A little bit too high. Number 4. Number 4, it says, find the coefficient of a x to the 10th in the expansion, parentheses 3 plus 2x squared to the 10th. Okay, so first thing we're going to do, we're going to write out the general term. The general term is n chooses r times a to the n minus r times b to the r. But in our case, we know some information. We know that n equals 10. We know that a equals 3. And we know that b equals 2x squared. Since we know all that, we can write out the general term much more specifically. So instead of n chooses r, we're going to write 10 chooses r. Instead of a to the n minus r, we're going to write 3 to the 10 minus r. And instead of 2x squared quantity to the rth power, we'll write 2 to the r power. We'll write x squared to the r power, and then we'll end up with 2 to the r x to the 2r. Then we are going to look at the x part of it. Do you see the x part of it in purple here? And then we see that, oh, they want the x to the 10th term. Well, the x to the 10th term means that this purple part of the x must be 10. So I'm going to solve that algebra equation. 2r equals 10, so r equals 5. We've just discovered what r is. Now we can plug back r into every other single part of this. So do you see how, like, when they give us the variable part, we could just like separate out the variable part and use the variable part to figure out what r is. Once we figure out what r is, we plug r back into the number part, which is this part, this part, this part. They're all numbers. So once we put the r value in, we can figure out exactly what number that is. So we put in 5 into 10 chooses r, and we get 10 chooses 5. We put 5 into 3 to the 10 minus r, which is, it would become 3 to the 5th. And then we put 5 into 2 to the r, so it becomes 2 to the 5th. And of course, when we put 5 into x to the 2r, it gives us x to the 10th, because that's why we chose r equals 5, because we want it to be x equals 10, x to the 10th. So now we take 10 chooses 5, 3 to the 5th, and 2 to the 5th. We multiply it all in our calculator, and we get this enormous number, 1,959,552. Okay? Whew. All right. Next one, part C. Now this is a different way of specifying it. Now instead of having x's only, now we have x's and y's, right? So we have a contribution from the a term of x's, and we have a contribution of the b term with y's. So let's write our general term again. So instead of n chooses r, we're going to write 6 chooses r. Instead of a to the n minus r, we're going to write 2x squared to the n minus r, which would be 6 minus r. So 2 to the 6 minus r, x squared to the 6 minus r, and then instead of b to the r, we're going to write negative 3y in parentheses to the r power. So negative 3 in parentheses to the r power, y to the r power. So you notice I took the subtraction sign and associated it with the 3 so that we could take care of that. Now, I distributed the r also. I distributed the 6 minus r also. Okay. Now let's use some of our clues. It says that x to the 6 and y cubed is the variable part of this equation. Well, the x to the 6th part comes from here. The y to the 3rd part comes from here. The y to the 3rd one is pretty easy to solve. We just equate y to the r with y cubed, so we know that r equals 3, right? Once we know r equals 3, we can just plug r equals 3 into every single r value here. We can figure out the coefficient. Now, you don't need to plug it into the x and the y to figure out the coefficient, but you could plug it into the x and the y so that you can make sure that you did everything correctly, okay? So, it would be, instead of 6 chooses r, we would put 6 chooses 3. Instead of 2 to the 6 minus r, we would have 2 to the 6 minus 3, which would be 2 to the 3rd. Then we have negative 3rd to the r, which would end up being negative 3rd to, negative 3 to the 3rd, negative 3 to the 3rd. Instead of x squared 6 minus r, we would have x squared 6 minus 3, so x to the 6th. Instead of y to the r, we have y cubed, so y cubed. So we can see that the variable part of it, x to the 6th y cubed, came out exactly as we needed it to. The number part of it, 6 chooses 3, 2 to the 3rd times negative 3 to the 3rd. If you type it in your calculator exactly like this, you would get negative 4,320. Be careful with the negative 3 because you do need to keep it in the parentheses, okay? Negative 3 times negative 3 times negative 3 gives us negative 27, by the way. Okay, we finished that one. Now let's move on to number 5, which is the last one. I know this is a very long video, and I know this is happening every single page of this thing, but I warned you, right? Okay, so first we're going to write the general term for this. So it's going to be n chooses r, 15 chooses r. X is the a term, right? The exponent of the a is going to be n minus r, which is 15 minus r. The b term is 2 over x squared. We're going to put it in parentheses and take it to the r power. Now, we need to focus on the x part of this because they said to find the constant term in the expansion. Maybe this is the first time you've done one of these, but looking for the constant term at the first time might be kind of tricky because you're like, well, I'm going to divide this into my variable part and the number part again. So let's say that the variable part, let's color it in green. The variable part is this part and this part, right? And then the number part, let's color in yellow, is this part and this part. So we want to separate it normally into the variable part and the number part. Now, how does that help us when we're looking for a constant term? A constant term doesn't have a variable part. How do we account for that? What we're going to do is we're going to take the green part and we're going to write it down here. And you see that we've isolated just the green part. So it'd be x to the 15 minus r in the numerator. In the denominator, I'm going to put x squared to the r power. I am going to combine these two x expressions into one exponent. So instead of 15 minus r and the x as the exponent of the numerator and 2r as the exponent of the denominator, I am going to subtract the two. It's going to be 15 minus r minus 2r, which is 15 minus 3r. Now, we know that the variable part of this is equal to nothing. So actually it's equal to 1. In terms of exponents of x, how do you make it equal to 1? Well, you set it equal to x to the 0. So x to the 0 is 1. So we know that the exponent 15 minus r minus 2r is actually equal to 0. So we are going to use algebra to calculate that. 15 minus 3r equals 0. 3r is equal to 15. R equals 5. Now that we know the r value, which is what we always need to figure out first, we're going to go back and plug it in again. We plug it into the original general term, and we end up with 15 chooses r, or 5. We end up with x to the 10th. X to the 15 minus r is x to the 10th. X to the 2 in the denominator is x to the 10th in the denominator, so x to the 10th cancels with x to the 10th. The numerator, 2 to the r, stays, is 2 to the 5th, right? And if we put the yellow parts in the calculator, 15 chooses 5 and 2 to the 5th in the calculator, we multiply them together, we will get 96,096. And what is the variable part of this term? It's nothing, because x to the 10th divided by x to the 10th is just 1. Okay, so there is no variable term. And that is finally it for page 5. Phew.